See, now I can't switch to a view and then check because I think this is completely filling up my desktop, you know. Hello? Is it? Yeah. Okay. 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 Yeah. Yeah. If something is not coming, just call me because I'm not looking at anything else, you know. Okay. Yeah. Yeah. Okay. Thank you. Thank you. Yeah, so I think everything seems to be how to work with Amazon Cloud and also DigitalOcean. I also wanted to show you how to work with Microsoft Azure. Okay. Hello? Yeah. Is everything coming properly? Okay. 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 Uh, okay. So I also wanted to show you Microsoft Azure Cloud, how to actually, it's more or less similar, but then as you can see yesterday, you know, the Microsoft CEO Satya Nadella was also saying that he will make for Andhra Pradesh government more cloud services available for the government, I think. So I thought I'll also show you how to work with Microsoft Azure Cloud. In fact, we're doing a startup company with the support from Microsoft Azure in the US, called Quantum Ventura. That the whole system is getting developed with Microsoft Azure. This is called PeertoPeer. One of the sessions here, I'll demonstrate what is the kind of stuff we are doing with Microsoft Azure Cloud and how we are actually bringing up this startup company with the Microsoft Azure Cloud support. But anyway, so before going further, I thought that I will actually give you a little deeper insight on cloud computing, not just working with the cloud computing, but then we also want you to understand the deeper aspects of cloud computing and what is the kind of research that's possible in cloud computing and what are the kind of some of the projects that you can do in cloud computing before we dive deep into Hadoop and start looking at how Hadoop works and then how okay. Actually, for the first time, we start seeing that, I'll be using, for this whole lecture, I'll be using the PPTs, okay. So far, I've been using the machine and teaching you only with, practically, only programs that run and live programs that I'm developing and then working and showing you how to work with systems. Today it's like a research focus. What further work is possible and what's the kind of work that we are doing. Okay. Some of the work that I'm actually presenting here has been supported by various. For example, the Cloudbursting work, which I'll be showing sometime during this presentation, is a joint work with Xerox Innovation Group in the US. This is a project that we started in 2008 on how an internal cloud, for example, a set of compute resources which are local, can be made to work with an external cloud like Amazon Web Services. Okay. So this is in 2008 when cloud was not still that popular. The term cloud was not still popular. We have been working on this framework called the Cloudbursting framework, and with a few patents also in this. Sriram Kailasan is a PhD mine now. He's actually a faculty member at IIT Mandi. Both Nathan and are with Xerox Spark now, and then they're part of this research that we did almost for 4 or 5 years with them. They're actually extending the MapReduce. I'll just take a minute. Just give me a minute. Sorry about that. Yeah, no, just had to cut off the noise that's coming from somewhere else. Yeah. So the second work that I'm going to show you, we're actually going to go deep on MapReduce, and we'll show you how to work with MapReduce with Hadoop framework. But one of the works that we have done, no, research works we have done for quite some time is how to extend this MapReduce paradigm itself. Okay, this was done with the Yahoo research support in the US, and this also led to actually setup of Yahoo Grid Lab in IIT Madras. Actually, Yahoo donated uh, a lab to IIT Madras, about 40 servers as part of this work. You know, I'm also going to show you that particular thing. And also, we also work with a company called Denibo in Chennai. Actually, this is a startup company started by the lab and along with two other IIT alumnus. This actually integrates the sensor devices to the cloud, and this company is called Denibo. They actually integrate the sensor devices over the network to the cloud, and this has been applied to variety of devices, variety of applications. For example, on the transport system, they use these sensor devices as part of the buses that are flying from Chennai to Madurai. And then these buses is moving, you can now send all the coordinates to the vehicle, so you know which route the bus has actually taken. So it can be a geofence. For example, the bus actually, deviating from the path it is supposed to be taking, then you can send an SMS alert to the owner or whoever is monitoring this whole thing. And also parameters like the vehicle, speed, at what, what is the fuel gauge meter reading, all this can be sent across to the cloud uh, every so often as the bus is moving. For example, you can program it saying that every few minutes or few seconds, if you want, this information is sent back to the cloud. On the cloud, you can do a lot of analytical. How well is the driver? Should you incentivize the driver? For example, is he driving it in a in a fuel efficient fashion? Then you can pay him more because that's where you save a lot of money. Things like, for example, one of the interesting fact that came out of this is the bus stops somewhere between Madurai and Chennai in the night, and then the fuel gauge dips by some amount. So you obviously can see this happens every day. The bus is stationary and the fuel gauge is dipping, which means that somebody is actually stealing the fuel from your vehicle. And this is a very interesting use case. Similarly, we put these devices in variety of other contexts. For example, vending machines, and then so many things. So this really opening up. If you basically look at the smart cities that people talk about, that is in one sense integrating the sensor devices to the cloud, and this can really open up large number of new applications environment where things can be optimized to a much larger extent than what we have been able to do, right? Then also, in terms of crowd sourcing plus, cloud computing is what iCompose is all about. It shows, how cloud and crowd can produce a lot of interesting results. For example, crowdsourcing is one where you actually have a lot of knowledge workers who become part of your environment. Things like, for example, you're translating something. Instead of machine translating, if you have a knowledge worker, you can pull in the knowledge worker, which is actually sometimes called the crowdsourcing. Crowdsourcing plus cloud computing can give you extremely interesting results. For example, Amazon has this crowdsourcing platform called Amazon Turk. Along with the cloud, Amazon Cloud, if you're able to use Amazon Turk, this becomes an extremely powerful mechanism by which the knowledge workers can be made to collaborate with each other in a seamless fashion with the cloud computing. We have actually developed something called iCompose, which is crowdsourcing plus cloud computing. This part of Pooja's work, internship work at Xerox. And also a lot of this assistance in the slide preparation has actually come both from Sriram and Pooja. Just to give you an idea, how the cloud computing is changing the world. If you look at now the growth of electricity in 20th century, it just started around 1900 with an electric bulb, first demonstrated in New Jersey in early 1900. Everybody was really excited when they saw this electric bulb. You can see the kind of excitement people had that point of time. Previous to that, people are using gas bulbs. Okay, now instead of gas, now it's kind of generating the electricity and using it for powering the bulbs. First, they actually made small electricity plants, which generate power to light houses, as opposed to gas bulbs, which when gas is supplied, we are now supplying the electricity from the small plants to power the lighthouses. Now, if you look at actually, then people they had actually small electricity generation plants, DC plants in their house. Then later they actually put DC plants for a few houses put together. Then AC, there is a loss in transmissions, and then the AC was supposed to actually reduce the loss of transmission and also other things. Then what really happened to electricity is now it became as a utility service, which means that somewhere the electricity gets generated and you actually consume it. An electric supplier for you, you just get electricity and then pay the bill. You never think of generating electricity yourself anymore, unless of course the standby when there is no power, then you have a generator, okay, and a diesel generator where you will use a diesel oil, okay, diesel to generate power for yourself. This is a standby mode. Don't actually use a diesel plant for powering your house because it's very expensive, as opposed to actually getting the electricity from the company which generates in a bigger scale, mass scale, and transmits it to you. The economy of scale. For example, now it's unthinkable for electricity. Whole thing is just a grid. You just plug onto the grid and then take whatever and also make sure that somewhere there's a peak demand, somewhere there is a lesser peak demand, then the whole thing gets evened out, right? Similar thing is what's happening to the computing. Computing is emerging now, the utility service. That's what actually the cloud computing is all about. Before cloud computing, what we have is, for example, very early reasonable when the Esther year made. But then people are accessing this computing over dumb terminals. There are a lot of dumb terminals which people are accessing the mainframes and doing a lot of their computations with these mainframes. Then came the client-server computing. There is a client is optimized for something, the server is optimized for something. For example, we typically look at the browser as a client. The running of the browser is optimized on the client side, and then the server side, if you're running a database, it is optimized for running the database load optimally on the server side. Okay. Then there is versions of this thin client, thick server, upsizing the client because client has more computing power. We went to all of those models. Okay. Then came the most interesting part of grid cluster computing. Since 90s at IIT Madras, we have this grid computing lab here. In fact, the Yahoo lab is called Yahoo Grid Lab. We've been working on this grid computing for almost last 15-20 years, and that's what actually the grid computing book, which you see published by Tata McGraw-Hill, actually carries all the work that we've been doing for the last 20 years in the grid computing research. This is available as if you look for the Jankiram under grid computing, you get this book, which is used by people now as a textbook for grid computing course, but then it's mostly evolution in the previous slide. Okay, and this book is now revised. It's available with computing plus cloud computing book, which is just about this now. Some of the work that I'm talking in the cloud space is available in that book, and that's one reason why I also want to touch upon that and then show you what kind of interesting research is possible in this particular area. Uh, Grid is nothing but, even computational grid is nothing but, putting together all the machines together on a network so that the resource sharing can happen. You no longer would like the resource to go idle. So if there is more load at one machine, you would like to shift that load to another machine and then get it executed in the other machine. So in some sense, the grid infrastructure, grid and cluster computing, that's what actually happened in terms of taking the machines together and sharing the resources across multiple machines. Okay, I think this was one of the most interesting things for us. Very early on in 90s, in IIT Madras, when I started my research, I've been working on how exactly I can have a local area network on which the Sun machines, Sun 3 bar 50s machines and 3 bar 60 machines can be co-sharing the IBM servers, and then they all can have a parallel load on them plus the sequential load. Okay, and this is one of the most interesting results in 90s that we have shown, saying that it is possible to do parallel computing along with regular workloads on these machines, and we actually demonstrated this on some 20 Sun workstations plus 5 IBM workstations connected at different places on our institute LAN, to just show how efficiently you can load balance the parallel load with the sequential load. To give you an analogy, for example, most of the time, fast foods are different from regular eating that we do, right? So before we demonstrated this result, most of the supercomputing either using normal workloads, and the supercomputing workloads are put on tray kind of machines. Now, for the first time, what we have actually demonstrated using that result is it is possible to actually mix both these loads on a number of workstations, that the idle computing capacity itself is good enough for you to be able to do a supercomputing kind of model. That means both supercomputing model plus the regular model coexist on the same cluster with the cluster of workstations. This is a very interesting paper. This paper is available as part of the book, and this is published in 1999 in IEEE Transactions on Software Engineering. The model is called Anonymous Remote Computing Model, and that's what actually we showed as part of the work that we did. One of the other very cloud computing is this peer-to-peer computing. Okay, peer-to-peer computing is different from client-server computing in the sense that there are a large number of cluster of machines which are all together as peers. So the idea is peers can come together and leave. For example, in our IIT Madras environment, we have an institute, storage sharing facility that is called actually the DC++. Okay, what this allows is people to share the files. For example, we have about 8,000 students. They all want to share, with others some amount of files and all that. So what they do is every machine donates some bit of a storage to the DC++, and there is a hub, which actually hub is one of the machines, and the hub has a metadata about what are all the files that are stored in this DC++. But then individual people actually contribute when they join this DC++, saying that I'll give 10 MB or 10 GB, whatever amount, that becoming a lot more important in the coming years, in my opinion. Though peer-to-peer computing suffered a bit in terms of Napster, which is a file sharing system, because of the reason that Napster violated some of the privacy laws. It led itself into some trouble, and it got some distribute to peer-to-peer systems. But I think in general, the peer-to-peer concept is the best concept for scalability and also for resource sharing, as opposed to any other kind of models that we have there, in my opinion. I think we are moving slowly to, as we said, virtualization, where the desktops, everything as a service. For example, last time we saw in the Amazon web services how we can create instances on the fly, the compute instances. For example, you can specify what is the memory, what is the RAM, what you require, and create it on the fly and pay for what is the amount of time you are using that compute resource. This is what we are talking as infrastructure as a service. You no longer want to own anything, like a cab service, which I was telling last time. You don't want to own a car. Okay, you own a car if every day you are actually moving around and you need a lot more, you put a lot more gadgets into your car, and then it is customized for your requirements, and then sorry, paying for all of that. Versus renting it. Renting something is more expensive, then you're going to buy it. Okay, otherwise you probably will try to look for the rent option. What is available now is a renting option for infrastructure, for software, for platform. We looked at all these models. We looked at Amazon Web Services, how to create a compute EC2, Elastic Compute Cloud, how do you create an instance of a compute instance. We also saw how we actually access, how do you start off our programs, how do we make the client actually, the same client server program we wrote for the Amazon Web Services EC2. We installed it, we allowed our client to contact that. Okay. We also showed you how to start an Elastic MapReduce cluster. This is a platform as a service. For example, if you want Hadoop as a service, soon we are going to look at how to do maps programming again. So when we are trying to do that, if you want to create an Elastic MapReduce cluster, it's simple. You go there and it becomes a platform as a service. You pay more. For example, one master node, 3 slave nodes. 10 slave nodes and one master to write your MapReduce programs. Use it, then release it. That becomes platform as a service. We also saw in the last class Salesforce.com, how Salesforce.com actually works. Okay. Giving the entire Salesforce as an application. So if your company has a lot of salesmen to be managed, this Salesforce.com gives you the entire application running. No longer what is the platform it is running, what is the hardware it is running. All that you will now do is take this application, create your own, as per your requirements, you only create few forms, and then you start working with Salesforce. That becomes application as a service. Okay, so all these models are possible, as we saw in the last class, and this is a classification. So slowly what's happening is computing is becoming as an utility. Okay, now to just give you what really is all this about. For example, computational grids distributing the computing power over distributed systems using different plumbing architectures. For example, previously we had this common object request broker architecture called the CORBA. Okay, CORBA was making objects pluggable anywhere on the distributed system. So you can actually, for example, this is a standard infrastructure. For example, in Jntuk Kakinada, I'm just actually plugged into my distributed infrastructure. So I can execute a method called bark on the dog. So I search for it, and then I just execute that method, wherever it is, it actually gets executed. This is what we mean by distributing the computing power over this infrastructure, plumbing architectures such as Corba. Uh, these are actually computational grids. What are data grids? Data grids actually store large amounts of data in cluster and grid nodes. For example, if you have terabytes of data, you no longer can store the terabytes of data in one single machine. You essentially need to distribute this data on multiple machines. This is where Hadoop kind of infrastructure comes into picture. Hadoop as a file system allows you to store a large amount of data distributed on cluster of nodes. Okay? On top of that, you have this paradigm called the MapReduce for processing the this large data. So you have data, large big data, plus the processing part, which comes together as a computational and data grid. That's what we will be studying in the next few classes when we're going to look at MapReduce actions for processing large amount such as web pages. For example, what Google does essentially, this paradigm started with Google. Google went and then crawled the entire web. Then they have the pages, whole web pages. It will be into probably now more than billions of pages, right? It could have probably reached 1 trillion pages on the web. Okay, I'm not sure exactly what is the count, but now you want to index these pages, which means that you want to understand what are the keywords in each of these pages. So you want to do some processing for the keywords, and then based on that you want to index. So this is if you actually see, this is these few terabytes of data for what are the keywords, how you're finding the keywords. For example, you see word count as an application. You just want to count the keywords, and based on that you want to index these pages. It can be done on one machine. What normally is done is by Google is a 1,000+ machine cluster on which they start processing this, and indexes, generates the proper indices, and that's how when you search for it and then pick the right pages for you and show those pages. This typically processing such large amounts of data, you can no longer write the programs as we initially wrote the client-server program for Java. If you want to write in a similar way, open a socket, try to open the connection and do all of this, simply not possible. That's where you need these MapReduce abstractions for processing large amount of data. There are extensions to this MapReduce. Some of our research work shows MapReduce is not good abstraction. It has its own limitations. That's where we improve it by saying a generate MapReduce is much more powerful and flexible than just the MapReduce abstraction. And we'll show you why that is in some of these classes here. Those are the kind of research problems one can. I'm going to indicate starting from now what is possible people can pick up and start working, and that's the reason why I'm completely going with slides in this lecture as opposed to just which I started with doing practical problems. Now I'm taking a much higher level view and trying to teach you what are the kind of different things one can think of doing in this. Okay. Now, if you look at computing as a utility, the basic thing is build versus buy decision. Instead of purchasing computing infrastructure and software packages, pay for actual use by using infrastructure as a service, platform as a we looked at this previously. This is a buy versus rent, buying a car versus hiring a car, building a house versus renting a house. Both can make sense, but then you have to decide which one is more appropriate model for you. And especially if software as a service, if you look at even Windows, one of the most important things, okay, you can pay, you can actually give a subscription for a year as a cloud service. Okay, wherever you are, you can connect to the cloud, you can access the office and can use it. Okay, and this, which is a very interesting model. Instead of actually buying Microsoft Office, probably paying a subscription and using it for a year and renewing that subscription may be much cheaper and better for you in terms of how you actually want to use this service. But that's what's really happening. Okay. What is cloud? I think this is probably the most interesting definition, and then this is what I would like to go with. Cloud is all about internet as a common bus for delivery of services. These services could be infrastructure as a service, platform as a service, software as a service. Okay, so key thing is the emergence of internet as a common bus services, which include compute as well as software services, resulted in this paradigm called cloud computing. When we say cloud, it is somewhere, we don't even know where. For example, when you start off an instance in the cloud, location of machine, all that we are doing is we are just accessing that service over internet, and that's what we mean as we are using internet as a common bus for delivery of services. Okay. A large amount of web data residing in the internet can be considered as residing in the cloud, because this is already, all your mail services, for example, Gmail services, right? These in the cloud. You are using the email as a service. You are using platform as a service. You are using application as a service. All these services are being actually accessed with internet as a common bus for the delivery of these services. Okay. Now, that way, cloud computing represents a new paradigm in which computing data and software are delivered as an utility service over the internet for the consumer on a pay-as-you-use basis. That's the key thing. We actually saw this. I'm only now giving a formal way of looking at the cloud. Okay? When these services are delivered over the cloud, if you're actually delivering these services internet, we refer this to as private clouds. Okay. The same, for example, in IIT Madras, we can have a cloud service where people can start off instances, but then only locally. They can have a storage cloud, they can have a complete compute cloud, and then we can use these services. Then it becomes a private cloud. So if these services are delivered locally over the internet, these are referred as private clouds. Okay. Now, I think this is something that we saw last time. This is called SaaS, software as a service. SaaS has emerged earlier as part of the service-oriented computing. We also have before this web services. Services published, services discovered by consumers, and bound to these services to utilize the services. So typically, all that we are doing is, in the case of cloud computing, we are just using web services over the internet. For example, we saw in the case of Amazon Web Services. I'll go over it once I finish this and link up what I'm doing with what we saw the other day in terms of what our understanding of the cloud computing is. Okay? This is the basic paradigm on which it actually works. Service providers, and these service providers put their services into a registry. The consumers go and discover these services, and they bind to these services and then use these services. The difference between computing and service-oriented computing is essentially this registry. In the case of cloud computing, there is no need for a registry. All that you know is the prefab services, and the consumers bind to this and use them. For example, if you don't know who is the service provider, then you need a registry and a search on the registry to be able to automatically discover the services, should be able to make use of them. This is one layer above, and we are still not there, because automatic discovery of services is still an unsolved problem as far as computer science is concerned. And once that comes, your running programs can discover what services they need and who is the provider of these services, and can automatically bind those services and can render the required services to the customers. Okay? That's a tall goal, and we are still not there as part of this whole thing. Okay? One of the key things between cloud computing and service-oriented computing is services are the building blocks. Okay, build a basic service, an API or registries. Now you can actually build more higher level services composing of these basic levels. It's possible to visualize the entire software stack as being built using services as building blocks. Okay, this is actually the service virtualization. So we have previously this COM, DCOM, CORBA and DCOM. Then it went into semantic web services. Now what we are seeing is virtualized service systems, and these are the mechanisms by which virtualized service systems, layers of services, are the mechanisms by which people are building very complex systems. For example, you can see the following as a software stack. If you include the hardware as well, then you have a hardware. On top of the hardware, you have the OS as a core kernel. On top of it, you have the OS modules. On top of it, you have the middleware stack. On top of it, you have the application stack. And this is an approach that could be useful in building open-ended distributed systems, since all the layers could be easily configured and adapted to this application requirements. Okay. One of the things that we are setting up, for example, the model for this, what we are setting up, for this course, the associated lab, for example, the Boss Mool lab, along with the Hadoop stack, you can see it as part of this. For example, the Boss Mool actually takes the OS core kernel and makes it into a service. What we have there is what is called the minimalistic object-oriented Linux as the core kernel. It exposes some services. We can easily configure the core kernel as wrappers. There are object-oriented wrappers all around the minimalistic object-oriented kernel, with which you can customize the core kernel. Core Linux kernel can be customized, and that is at one layer. At the next layer is operating system, which is in this particular case a distribution, Bharat Operating System Solution, which is a CDAC distribution. Now on top of it comes the middleware stack. The middleware stack in this particular case is the Hadoop stack, because you are doing the MapReduce programming. That's where the Hadoop stack comes into picture. Okay. Now on top of it comes the application stack. For example, whatever analytics applications that we are developing will come as an application on top of it. For example, if you generate MapReduce, it becomes a different kind of an application. You're doing K-means clustering, it becomes a different kind of an application. So you have the entire application stack. What you should understand is the power of this mechanisms and the lab that is setting up for you is it is possible for you to customize at each of these layers. For example, the last sentence is very, very important here. Such an approach could be very useful in building open-ended distributed systems, since all the layers easily reconfigure and adapt to the application requirements. For example, your application needs a certain kind of file storage, a certain kind of indexing. All that is possible to be adopted at the core kernel level by changing the filters that you use at the core kernel level. One of the very interesting projects that you can think of doing is when we do the MapReduce programming, you start seeing that MapReduce actually divides the file blocks, okay, into multiple nodes, and these are stored there. Now there is a read-write performance that happens on each of these nodes. Now you want to actually, this is like, you have 5 people. I'll give you an example. Okay, there are 5 people to whom you are actually distributing. Let us imagine, I'll give you a simple example for you to understand. Okay, I have a large 1000-page book. Okay, some 1000-page book. Now I want to count the number of keywords. Okay, I'll give you a specific set of keywords. What needs to be done is now you need to count the number of keywords occurring in these 1000 pages. Now, how can you easily parallelize this? You can actually divide these 1000 pages. This is one big file. Then you can't store it, let us say, with one person. One person cannot handle this. It is so huge and so massive that one person will not be able to carry it. So you have to divide it. Okay. Now let us say I divide it into 100 pages. I take 10 people, I divide it 100 pages for each one of them, and then start, okay, distributing 100 pages to each one of them, and each one will count whatever number of keywords. Then I will have somebody pulling up all these results and putting finally something together for me, the numbers. Okay. This is typically how MapReduce will also work. We'll see that as we go into MapReduce. This is the kind of distributed programming that you do. Okay. Now this is a very typical Hadoop stack. Okay. Now let us say one person in this, 10 people, some of them are very stout, they can carry more. Some of them are very thin and lean. I used to be very lean, okay, and I'm still probably still lean even now. But then there are some colleagues of mine are really stout. Okay. Now, if you want to distribute the work based on the weight of the person, okay, so that how is that possible? Then you should know, for example, while they are doing it, somebody is doing faster, somebody is doing slow. For example, somebody read-write performance is very bad. He's not able to read and write quickly. Okay, you want to sense this in real time and wants to adjust. For example, instead of giving 100 pages to each, as these things are happening, you want to distribute a different amount of load to each one of these nodes. That is possible in Boss-Mool stack. Okay, this will be a very interesting project for the students to pick and do, and this can really open up a very interesting dimension of how one can do heterogeneous, on a heterogeneous platform, how one can improve the performance, okay, of MapReduce. That is a big data analytics. Okay, such an approach, this is the key thing. Such an approach could be very useful in building open-ended distributed systems, since all the layers could easily reconfigure and adapt to the application requirements. Okay, some of this we are going to see as we go forward. Okay, now the integration of the third-party component services is also very critical as part of the, for example, this is not part of cloud, but then essentially cloud needs to provide a way for getting the third-party services to be integrated into software. For example, now you see SMS as a third-party service, right? Nobody, and the actual software developer doesn't own the mobile. Be best done by service abstraction and bringing the cloud computing paradigm to the next level. Okay, I think I'll stop here. This is possibly, before I go further, next class I'm going to go a little further. Next 3-4 classes, I'm going to show you, for example, what is one of the key things why this whole thing became very viable, or cloud computing came in, is most of the servers are purchased by the few big players. For example, Google, Yahoo, Microsoft, Amazon. Okay, large data centers in the US have more than 50,000 servers. Each of these actually owned. For example, why this whole cloud computing started in Amazon, commerce company, right? In the peak of the time, their loads are really high, and to cater to these loads, for example, these loads are extremely high. Right? That's the time actually they get the peak business. Okay, for the peak business, when they buy the servers, when they it's a lean. Most of the other time it's lean. Most of these servers are idle. That's where once they move to these web services, they could open up, say that I have so much of servers available, anybody can rent it and can make it. Okay? And you should also realize that more than 1/3 of the cost is in electricity for powering and then air conditioning. Okay? Estimates of data center utilizations range from 5 to 20%. So there's large amount of excess capacity, and that's the reason why this cloud computing became a very interesting paradigm as we saw it. Okay. Right. Um, and also, if you basically look at the emergence of this cloud computing and also software as service, as we saw previously, the LR services, okay, that means you can expand as you want and you can reduce as you want. This is the most interesting part of the cloud, and that's where we are actually seeing this whole paradigm get into very nice strides. Okay, before we go further and see how the this whole thing works, I'm going to shift now and then connect up with what we did last time with the cloud computing thing. Okay, uh, we actually I'm also going to show you, for example, the uh, Azure Cloud, also Microsoft Azure Cloud. But then as far as today's class is concerned, I'll just go back to the Amazon Cloud, okay? And then connect up what I'm talking and giving you some more directions in terms of how this whole thing is working. Now you see this is a web service, aws.amazon.com. This is just a web service. This just takes me here as a web service. They have actually published this as a web service. All that I'll do now is I'll just go here. There's this is actually Amazon Web Services. As the title, it doesn't say cloud services. It's actually a web service, and this is being provided over the internet to me, and that's how it becomes a cloud service. So I just log in here. Now I just go into my web services. The number of web services that this Amazon provides for me, okay, is what I'm actually making use of, and these EC2, which is actually the virtual servers in the cloud, elastic compute cloud. Okay, EC2 is the elastic compute cloud. Okay, you just go here. This is what you are doing. This is one web service that is being provided by Amazon. Okay, the whole infrastructure as a service has been abstracted and provided this as a service to me. So when I go here, I can now start start my instance. Okay, and this becomes infrastructure as a service. Okay, any number of instances I can create. I can increase the number of instances, reduce the number of instances. That becomes now the elastic part of it. For example, I have 0 instances running, 0 volumes running. So all that I'm doing is I launch an instance now. Okay, this is again a web service. As you can see, this is just everything is over internet. Okay, now we are selecting a particular machine and we are saying now this is what should be launched. Okay, I'm saying a general purpose T2 micro instance is what I want to launch, and this gets launched. So now this instance is launched. Okay, now this is the SSH pair with which I'm actually launching this instance, and this instance gets launched. Okay. Now I've actually launched this instance. I will start going there. Look at this. Now this will show me everything being virtualized is. For example, this is what I'm talking about. Everything has to be configured. Everything you need to understand, and set it up. We are setting up everything. Now this instance is sitting somewhere inside the network of Amazon Web Services. I don't even know where it got started. Probably I can create this instance here or somewhere else. See, this instance is still this instance is basically the 54 this IP address 210.30.26, and now I can SSH to this. Okay, this is how I'm actually logging into this machine. Okay, this I'm pasting now, and I should be able to log into this machine. Okay, connection refused. As you can see, this is the problem now. I've started the connection, but then is this allowing the connections? Okay, did I start with the corresponding for example, look at the launch wizard here. Okay, the security that I provided while launching this instance. Unless I actually provide an ability to connect to this instance, I possibly won't be able to do that. Okay, These are all the things. What is the virtual ID of this machine? Whether is this allowed, not allowed? Okay, for example, here you can see the inbound traffic. Okay, this is still allowing. I don't know why the I'm still not able to connect. But then it's possible that sometimes. Let me make it all TCP. This I did last time. Okay. Now let us see if it just goes up, and then I will be able to connect. This is actually essentially the compute cloud. Okay, I can fix it. Okay, so this gets connected now, as you can see. So there is a problem with the public key. I think it should be somewhere here. So this should work now with this. Okay. You need to figure it out a little bit, but then this is now I'm on that instance now. I can do whatever I want. Last time actually I showed you how to transfer from my local machine my Java files here, make the client remote there, run here. Okay. So this is what is a EC2 compute cloud instance is all about. Okay. Now if you actually go to other web services that are available here, now you can see there are other services as part of this. For example, we saw the S3. S3 is simple storage server. Okay, S3 simple storage service cloud. Okay, you go to S3, you can store any data there. For example, you can create a bucket, transfer your data into this bucket, and specify now what you want to store into that bucket. So this is what becomes the storage service. EC2 is actually a compute service. Now S3 becomes a storage service, which is provided again by the web services. Okay, right? Service for me. Okay, I have some examples for Hadoop MapReduce stored here for doing the assignment. Okay, a 10 node cluster, 20 node cluster, 100 node cluster, and you can start. For example, these are the clusters that I did. Started clusters. For example, you can say create a cluster. You can create a 10 node cluster or a 100 node cluster, and then do your MapReduce programming on this cluster and go off. Okay. I'm trying to make the BOSMOL cluster available for all the colleges in the cloud, and see if this can be, we can actually make this cluster for doing the assignments. It involves some budget, so we have to see where that budget is going to come from. But once we say that create the cluster will be done, and then the instance will be available in the cloud for you to be able to do this. Somewhere down the line, we are going to show you how to do elastic MapReduce on the Amazon cluster. Okay. You can also create an RDBMS. This is what we are saying. If you do the Dynamo is basically the NoSQL database. Okay, this is something that you can create in the Amazon cloud. Okay, we'll also show you how to create a NoSQL base in the cloud and work with that cloud. Okay, and we are also going to show you, for example, how to create a relational database instance and work with that relational database. For example, IIT Madras has this database course, in which again we give the entire database software for doing the assignments. We give 3 assignments as part of, we actually now do certification under that actually colleges as well. We did for the Kakinada Institute of Technology, actually is one college that had set up the BOSMOL lab, and it actually had a database certification course that was done for them from IIT Madras. Okay? The idea is to again give this as part of a cloud service, so that each student can have his virtual instance in the cloud and can do the assignment in the cloud, but then obviously much better reason to set up a lab in your own college and then do it as part of that. For example, this is a NoSQL database that's possible to actually use it. Okay, then you have the RDBMS. Okay, all these are possible. These are all web services. This is what we saw last time. The last class is what we saw. And if you go to Microsoft Azure Cloud, you get a similar service, set of service. Slightly the interfaces are different. I'll show you once how you can actually work with Microsoft Azure Cloud also. Okay. One of the key things that I would like you to think of, next few minutes I will use it to tell you a couple of other projects. One of the interesting projects that you can think of is DynamoDB. This is actually the NoSQL database that we can start off, and we can fully manage non-relational database services. Provides fast and predictable performance with seamless scalability. Okay, these are interesting things that they have. Okay, let me not go further on that. I will actually come back to this here, and I will actually stop the desktop sharing. And last few minutes I want to spend on what is one other possible project that people can do. Okay, one of the other possible project that students can think of is, for example, we moved the client-server software. For example, we wrote a client and we wrote a server, and then moved it eventually to the cloud. Okay, one of the most interesting thing that's happening now is people have to migrate their applications to the cloud. Like what we have done in the local area network, we want to migrate those applications to the cloud. Now, does there going to be significant architectural changes that you would like to do or you would like to make? And what are the kind of potential architectures, okay, for migrating a local application into the cloud is an extremely interesting project for people to do. For example, in the cloud, you will never know where the server instances will be running. Okay, and you also won't know how you will be charged. For example, compute time is always much cheaper compared to the data transfer costs. Now, I will show you a Twitter application. As I was telling you, with Microsoft Azure, we are actually developing a one startup company in the US, in the Valley, okay, the Silicon Valley, on actually something called a company called Quantum Ventura in the Silicon Valley, which is using the Microsoft Azure Cloud. We have a tie-up with Microsoft Azure to actually in developing this. The whole idea is, as the Twitter feeds are coming, you would like to do a lot of analytics on this Twitter data. One of the key things is there are multiple servers involved in this, and the application runs with multiple servers running on multiple data centers. Now, for example, as the application is pulling the Twitter data, there's a charge involved in actually pulling this data. And further, we store these tweets into some backend machine, then again, the data transfer is actually charged. What typically in a local area application, if this application is running inside my LAN, none of this will be charged because I assume a high-speed network and I won't be paying any cost for these data transfers. Whereas in the case of a cloud, the architecture has to be completely different. I'm going to show you, how this architecture, what is the pricing of this architecture, why this will change completely when I move this application into the cloud, and why I should be aware of the cloud architecture. How do you migrate applications into the cloud? You can take small applications, and start thinking of even a database, small database application, and start migrating that to a cloud. This could be a very useful, project for the students. Somebody is trying to go slightly deeper and go to a research level, then one can think of a research project in terms of looking at cloud architecture or patterns, okay, software patterns or design patterns for architecting applications in the cloud. What are more useful patterns for architecting applications in the cloud? Okay, this can be very interesting research project. One of the things that coming and then doing this course for Jntuk as two parts to this whole story. One is to make you actually be more hands-on people. You sit and should be developing things. The other part is you should be extremely creative and should be looking at problems that help you actually pick up very innovative problems and should be able to do good student projects. And some of the faculty who are learning should be able to pick some research ideas and see how they can do research in these areas so that the research ecosystem is also improved. So we're actually aiming at multiple these things as part of the course, and that's how we would like to develop this, not just writing an exam and passing an exam. Don't look at this course as something where you're just doing a regular course and then you just write the exam and you got so many marks. I think that's important. No, but then more than that, what is more important for you people should be thinking, understanding the concepts fundamentally, thinking of actually using these concepts practically, and also looking at creative and innovative ideas, and the highest level looking at what are some of the good research problems in this particular area. This is, I think, the focus of this. Next class, I'm going to continue this trend. Next 2-3 classes, I'm going to do this. And the title of these lectures is roughly Emerging Trends in Cloud Computing and Big Data. Okay, those are the slides that I've made, and I will be doing those slides in the next 2 classes before I switch to a Hadoop kind of, how we will program in Hadoop and teach you what is Hadoop and how do you program MapReduce in Hadoop. Okay. Any questions you have at this point? I can take few questions, and then we can actually see how we are going. Okay, I have another meeting shortly coming up, so I can spend about a few minutes, roughly 8 to 10 minutes, okay, on this before I sign off. Okay, any other comments, questions you have, you can put it in the chat box. Okay, right. Any questions? I also want to list a few projects, possible projects people can think of doing as their final year projects. I think is my assumption right? Most of these are final year students attending these classes. What is, somebody is asking, what is the role of NoSQL DBS in cloud computing? Okay. See, NoSQL, for example, things like Cassandra are extremely scalable. Okay, they're best created in the cloud. You can also create them in the local. Whatever can be done in the normal environment can be done in the cloud as well. The most important aspect of cloud is the auto scale. As the load increases, the cloud provides you with an infrastructure by which you can auto scale. For example, today you have a gaming software, and then it is being used by 2 people. Tomorrow, the game becomes very popular and 1 million people will start using that game. Okay, then your whole infrastructure, backend infrastructure should be scaling. Okay. Now, one of the things with this Twitter also, we are trying to now test it with a few million simultaneous users. That's another very interesting project. For example, you want to test the auto scale in the cloud. How will you develop models for auto scale testing? For example, if you are able to develop a simulator for testing applications in the cloud, that's what quite a bit now. Okay, because those are the interesting things that are emerging as part of the cloud ecosystem. Okay, right. I hope that answers the question. Okay, any other questions? Yes, I think Kakinada is, I think, to raise. I will sort of get them for the interaction. Okay. Yes. Sir, we'll work on Amazon Cloud for our assignments. Who is actually asking this? I think you have the Bosmol stack with one node and then 3 or 4 machines available there. So you probably may not work on the Amazon Cloud. If you want to work on the Amazon Cloud, you have to pay. Okay. Amazon Web Services is a paid service. It is not a free service. So you have to start your accounts there, then you will be paying. Right now you won't be doing your assignments with the Amazon Cloud. Right? You can start the free, they have some free tiers available. Let us see if you can get onto the free tiers and then can do your assignment. Okay, but as it is, we are not trying to actually have the assignments directly done by you in the Amazon Cloud. Okay, but then you can start your instances in the Amazon Cloud, and then you can start experimenting with it. With the introduction that I gave, you should be able to start your, I think your Vijayanagaram campus has already started a digital ocean. Last time I saw they were running something in the digital ocean. So I think probably Jntuk Moocs probably may be able to do something and set it up for you. Okay, we'll work. We'll see where the assignments are going to be done by the students here as we go a little further. Okay, yeah. Okay, any other question? Yeah, if you have no other question, one of the reference books that I'm actually going to use from now onwards for the next 4 or 5 classes is this grid and cloud computing research monograph being brought out by Tata McGrail. I give the reference to that, which will talk about how MapReduce optimization is possible. How do you do MapReduce programming on large clusters? Okay. Some of that material I'm going to do it in the next couple of classes, but this will have more advanced material. But the idea of this advanced material is make you expose. Okay, make you expose. There is one other Stanford professor who is actually teaching the cloud computing course, Timothy Chow, who visited me. Okay, he has this web reference called computing technology. He gave a complimentary access. This is a book access that he gave it to me. I was going through that. It is more like a material with some reference content available. I'll probably again share that with you so that the college can get an access to the reference material and can use it. Okay. This is the course in Stanford, how they're running that course. He shared that with me, and in fact he was in my office a couple of weeks back, and then I had an interesting discussion with him. If possible, I will try to have him do one lecture for you. I'm trying to organize a few series of lectures from experts so that you may be able to get some outside view of how this whole cloud computing is changing the world. As you can see, yesterday's Digital India campaign, Microsoft CEO Satya Nadella actually brought up that they want to focus, especially for Andhra Pradesh. I think the Chief Minister is pushing quite a bit in the cloud computing area, and he wants to actually take a lot of things to the cloud. In fact, he mentioned some school in Srikakulam getting connected with some other school over Skype and things like that. In fact, for most of you colleges now, we are coming over cloud. This is actually a cloud computing course over cloud, because I'm actually coming over cloud to you. I'm not physically present there. This whole class is being rendered in a cloud fashion. I'm not physically present at the location, but doing a cloud course. And if this succeeds, this model succeeds, possibly a lot more possibilities will emerge. And from that sense, I think Andhra Pradesh government is suddenly, I think some school, right? Gayatri school in Vijayanagaram or something. I don't know. He mentioned it's Srikakulam, so I'm not sure. I think a lot more interesting things are possible. Interesting projects are possible. Interesting government projects are possible. So I think this is suddenly a very important, direction and course, and then research thing, many colleges. So we hope that they will benefit from these lectures and they will be able to take things. Somebody is saying, how can we implement smart schools through cloud computing? Yeah, I think no, this is in some sense right. So, for example, you can sort of if the internet access is available, if the internet, I think there are multiple ways in which the cloud computing can be pushed to school education, and that's where the maximum number of things will change. For example, one of the very interesting thing is to bring experts to the school. Now how the live lectures are happening for you, the same thing can happen at the school level. It can be a lot more, a lot more effective. And also, for example, if you look at the Khan Academy model, where if you don't understand a concept, you can just go there and look at that concept. You can actually put good animation, stuff into the cloud, so that people understand. People can have more effectiveness in terms of learning the concepts, right? So there are multiple things that are possible. That are possible. Somebody is asking, please suggest data mining projects with cloud. We will actually do smart analytics in the cloud. That's part of the course. So we're going to look at down the line some projects in that direction. Okay. Yes, I think what was mentioned again in Satya Nadella's speech is that the government is to track the dropout rates. Okay. They are trying to, but then more than the dropout rates, possibly you can actually monitor. For example, one of the most important things that we should first do is that the school education should become better, which means that we should be monitoring what's happening in the schools live. Okay, which means that we should put online cameras, and we should connect them up, and we should monitor if the student is learning, whether the teacher is teaching. Okay, most of the time it is possible now what the teacher is teaching can be archived and can be even later by people to help the teacher improve, the student improve, so many things. I think that's how the maximum benefit can be reached to the schools, because there could be an offline analysis of what's really happening in the schools, unless at the ground level we improve things. Okay, unless you have ground level changes happening in the schools, not much can be happening. Okay, most of the schools can be wired, and then all the what's happening in the school can be easily logged in the cloud, and then we should take and see if there's a more dropout rate in a particular class. We should be able to actually monitor that, and we should be able to see what are the reasons for this drop in the schools. This is similar to what I was talking about, the IoT devices that we connect to the cloud. That's part of the company that IIT has incubated, right? So where the bus is moving, and we actually collect the data about the bus, and then we put a geofencing, and if the bus is deviating from the path, the owner is automatically notified, and then if there's a fuel theft, we can automatically detect it by doing the analytics. You can see good behavior of the driver, then you can incentivize the good behavior. Okay. Now, for example, in the school education, you can easily monitor the schools in the cloud. Put the school in the cloud, and then you can monitor what's happening in the school, and then you can incentivize good teachers, and then sort of penalize the bad teachers. So all this should be possible, and those are the things which will bring more transparency, more benefits. All these things should be possible. Okay, right? This yeah. So I think more of this information we can share as we go along. Now I think I should be leaving because I have another meeting coming up. Okay, so I think we will see in the next class on Wednesday as we go along. But one of the ideas is also to actually give you more ideas. As I'm saying, this lecture is not just No, to give you the concepts. That anyway is part of this thing, but also make you to think what's happening, and also expose you to the latest developments and the companies that may be interested in further talking to you, and then if you're interested in doing a project, how that can be made accessible. Okay, right. I think with this I should sign off now. I will come back on Wednesday.